Hey there, Dr. B here, and we're studying waves. Why? We're within the topic of the electron, and we're going to make the case that the electron is part matter, part energy. Energy oftentimes disperses itself in waves, and so we're going to begin by studying waves a little bit. This is a little bit outside the field of classical chemistry, to be sure. We're not studying matter at this point. It was observed in the 19th century that light passing through two slits can produce multiple lines, which is impossible if it's traveling in a straight line. This was the work of Young in the 1850s, and the conclusion is just like happens with water as it passes through, say, a hole in breakwater, light does travel in waves and can create interference patterns. This is strong evidence that light is traveling in waves. If it does, and it does, it must have a wavelength, an amplitude, and a direction, and a speed, right? The wavelength is clearly the length of the wave. The amplitude would be the height. We're not going to talk about that much. The frequency would be how often it passes a fixed point, and it would depend on its speed. We will assume its speed to always be the speed of light, which is 3 times 10 to the 8th meters per second. This leads to the speed of light formula, where c is the speed, lambda is the wavelength, and the frequency is given in how often, per second, for example. And since we're traveling at the speed of light, even very large waves will have an incredibly high frequency. Let's solve a simple problem using this. If the wavelength of green light is 522 nanometers, that's its wavelength, what would be the frequency of it? Well, it sounds like at first that we don't have enough information to solve this, but don't forget the speed of light is fixed at 3 times 10 to the 8th meters per second. I would rearrange this to solve for frequency. It should be the speed of light over the wavelength. Be careful because this is nanometers, but that means 522 nano, which is 10 to the minus ninth. So we'll just simply write it as 522 times 10 to the minus ninth. That should be an exponent in meters. Cancels, gives us 1 over seconds, and that would be the frequency of green light. Notice it's 10 to the 14th times per second. Very fast. Let's also take a look at the electromagnetic spectrum. Let's consider which wavelengths of light are dangerous and which wavelengths of light are safe. A nice dividing line would be the visible region. This is considered safe, but once you get beyond violet, you go more frequent, shorter wavelengths, into the ultraviolet, X-ray, and then even gamma rays. So dangerous side, safe side. And don't forget that this is essentially all possible wavelengths of light. These are the only wavelengths that we can see. Just a tiny little unit here, but you need instrumentation to measure all the other ones. So next to violet is ultraviolet. It helps to know that violet light is at about 400 nanometers, red is about 700. That allows you to say, oh, we're about to go into the ultraviolet over there, more dangerous. We're about to go into the infrared over here, safer. And that's how it looks like. This is right here. Now we're starting to tie it into the electron, the hydrogen emission spectrum. If you take hydrogen gas, put it in a tube, and then run a current through it, you will see that this plasma produces 4 visible sharp lines of light. There has got to be some useful information within that. We'll tell the story behind that and how that led to the discovery of where the electrons are around an atom. This is a study of waves.